Hello, hello. Does anybody hear me?
Yes,
Hey, thank you. Thank you for your feedback.
you're welcome.
Okay, the streaming has started. And today we shall go on with the modeling procedure. I recall you that we have seen up to last week the first 7 steps up to calibration. And today we will give a very quick look to the last step, that is validation. I anticipate you that none of you will be able to do a real validation of the model that you're going to build, but validation is always uh, auspicable because validation makes your model, we say, robust model. What is validation? We mean by validation a test of the calibrated parameters with a set of independent data. Independent from what? Independent from the data that I have employed for calibrating the model. I recall you that when I have a calibrated model, I have a model that is behaving in a more or less close way, in a more or less similar to a system I'm modeling to. The validation procedures, I am start verifying that the model as it has been built is working more or less as I'm expecting, and in particular, by having a validated model, I can make sure that the model I have built for a particular system may be applicable to several other systems, but similar, or the same ecosystem, but in a different period of its development. This is a fundamental step if you want to obtain a commercial product. If you are a modeler and you're building a commercial tool, like for example, ModFlow with very sophisticated models for groundwater system and so on. First of all, you build a model, you calibrate it, and then you pass to the subsequent step, that is a generalization step, that allows you to verify that the model works well for a similar system or for the same system in another period of its development time. Validation is always desirable because this is a final check, and in particular because this is a check that your model is robust enough to simulate even systems that were not the ones you employed for calibration. In general, the data that you employ for validation should be different, totally different from those used for calibration, and on the greatest number of possible forcing functions. What I mean by when I say that the data shall be totally different from those used to calibrate the system, this means, in statistical terms, that the data I employ for validating my model shall be statistically independent from the data I've employed to calibrate it. So it is expectable. You may expect that you calibrate a model, and when the model is still working well, you may say validated with the same system in a different time period. But this, of course, it is not a very strong validation, because this means that the data you are employing are somehow statistically correlated with the data you employed to calibrate it. Different is if I build up a general, for example, lake ecosystem model. I calibrate it on a specific ecosystem I'm studying, and then I validate so that I have a tool that may be applicable, for example, to several lake ecosystem models. You have already seen an example of a lake ecosystem, so You may understand what I mean by that. Again, the criteria established for checking that the model is validated are based on the model objective, as it is always the case, and in particular on the quality and on the quantity of the data that I have available. So validation is the last step, and as you will apply to a case study we will proposing you in the MATLAB classes, you will discover that you may find a way of validating your model by applying data coming from, for example, different seasons of the systems and modeling. And if the model is still working, then the model may be said to be validated. You understand that there are different levels of validation. A model, a commercial tool like ModFlow is a strongly, robustly validated model, but is in principle applicable to every groundwater ecosystems. This is in particular for ModFlow. There are similar models for other type of ecosystem, like for example, like lake ecosystems and so on. The topic I would like to discuss today instead concerning the procedure for building an ecological model is that of constraints. You may recall that when we introduced the system specification, beside the differential equations, these are systems of differential equations. I recall you that this symbology here, x underscore dot, means the space, the vector of the state variable. The first time derivative of a vector of a state variable is equal to a vectorial function f, but this function of state variables of the parameters and the inputs, outputs, and times. Well, I recall you that the last systems of a system specification is the one that allows us to reduce the degrees of freedom of my model by, for example, allowing us to algebraically express one of a variable as function of the other variables. We may identify three general types of constraints that may be applicable to ecological models. The three types of constraints are topological constraints, physical constraints, and ecological constraints. We may say that in general, all these constraints derive from conservation principles, and I will try to make this assertion clear during the lecture of today. As we will see in several cases, if I have a conservation principle holding for my system, and I recall you that conservation principles are principles of a maximal generality derived, for example, from thermodynamics. In this case, I have a tool that allows us to express one of the state variables as functions of the others, and this way I'm reducing the degrees of freedom of the system. And somehow I'm reducing the complexity of my description, and I'm building a tool that is much more treatable from a computational point of view. So let's start looking at the constraints. In particular, let's start looking at topological constraints. We have already seen some example of topological constraints. In particular, the first topological constraints that it comes to my mind is the one that we obtained when we realized that ecosystems are bounded systems in the sense that they show a delimitation of an area, so we may identify size for the system, and that we may include in my description boundary condition. I recall you that the environment may be subdivided into two parts: inside the system that is secure and stable, and outside the system that is stochastic and uncontrollable. With a topological differentiation, for example, allowing us to distinguish between inside and outside the system, and this has to do with topology. For example, we have several topological constraints, for example, area, mass, fouling, or structure of the systems may all induce topological constraints. For example, fouling is the process of organisms that colonize surfaces, for example, in water ecosystem. You may recall, if you look at clams, you see clams typically grow in colonies over solid surfaces under the sea, and the area that is available for colonization by these organisms may be considered a topological constraints. So a kind of limitation in the area, or maybe you may imagine on the mass. Another topological constraint, for example, is that is linked, is that the one that links, for example, the size of an animal and its metabolic rate, so the energy consumption per unit time, unit volume of the organism. Is another example of topological constraint in which we have a linkage between one characteristic, but maybe is the size of the organism, and another characteristic, but is its energy consumption per unit time, unit surface, unit volume. The mother or most relevant of all the topological constraints we may include into our description is that of conservation of matter. I recall you that we said that we formalize mathematically the conservation of matter by writing a continuity equation. For example, here I'm writing a continuity equation in which I say that the volumes times the derivative in time of the concentration of something is equal to what goes in minus what goes out, plus formation of new matter that is locally formed by internal ecological processes, minus transformation, that is elements of C, of matter C, that is transformed in something else. We may recast this continuity equation by, for example, writing in terms of production that the net production of an ecosystem may be equal to what ingested food into the organisms, so the food consumed by the organisms, minus those quotas of energy that the organism employs for living, for staying alive. In particular, we may subdivide this negative contribution as respiration or excretion or food that is lost during the process of assimilation, so not assimilated food. For example, we have seen, we have talked about efficiencies in energy transformation, and we may write as a definition that the efficiency in energy transformation may be explicitated by the ratio between the net production that I have just defined divided by the ingested food. So I have kind of percentages that tells us how much of the ingested food is converted in new organic matter, that is production. This conservation, this continuity equation comes from the energy conservation principle. And I recall you that the energy conservation principle is a formalization of the first law of thermodynamics. I give you a very brief overview of these laws. First laws of thermodynamics is defined by saying that if I introduce a state variable U, internal energy, and I recognize that the variation of the state variable du is equal to the variation due to heat exchanges minus the variation due to work exerted onto the surrounding of the system, this quantity, internal energy, is a thermodynamic potential. Sorry. So the internal energy is a thermodynamic potential. We have said that it is an exact differential mathematical thermodynamic potential is an exact differential, meaning that if I want to evaluate the difference of internal energy between two states A and B, I may simply calculate the integral of the variation of a state system from state A to state B. So I make the summation, infinitesimal summation of variation of internal energy, and then finally, by applying this integral, I obtain the variation, the difference of internal energy from state A and state B. We will see soon that this has some implications. We know from thermodynamics that this law of energy conservation holds for all transformation that are reversible or irreversible processes. You may recall that in thermodynamics we distinguish between reversible and irreversible processes. Reversible processes are processes that cross all states of perfect local equilibrium, the thermodynamic equilibrium, while irreversible transformation are transformation that cross also states of non-thermodynamical equilibrium. In this case, the energy, the first law of thermodynamics tells us that independently from the fact that the transformation are reversible or irreversible, I'm always able to calculate this integral that gives me a state function describing the differences between the states A and B of the system, and I obtain a thermodynamic potential. In order to demonstrate this first law of thermodynamics, I shall recall you the Joule's experiment that has established the equivalence between heat and work. I recall you the experiment was made by putting a liquid into a dewar. A dewar is an isolated system. And for example, I include a system for transforming kinetic energy due to the fact that there is a load that is by gravity going toward the bottom part of the system. This makes turning the pallets inside this dewar, and by this experiment, I can establish that there is a variation of the temperature, and by this, I can calculate the mechanical equivalent of the calories, and I obtain this figure that is G equal to 4,186 joule per kilocalories. And this is the constant that allows me to convert from mechanical energy to thermic or caloric energies. This experiment that was carried in the late parties of the 19th century was a very, very sophisticated, difficult experiment, in particular at that time, because it required to measure temperature variation of the orders of tens of Celsius degrees. So it required very sophisticated ways of measuring temperature. By applying this energy conservation principle that allows us to evaluate how mechanical energy may be transformed into caloric or thermal energy, we realize, or we more precisely, we formalize the fact that energy is transformed. So we introduce a different perspective in which we not only look at the quantity of energy, but it becomes evident that at least in ecological systems, there are different qualities of energy. How can I formalize and evaluate the different qualities of energy? Typically employing the energy coming from the sun. We know that all the basis of the energetical basis of all biological production on the biosphere comes from the sun. So we have that corresponding to a decreasing quantity of production, I may associate an increasing quality of the energy produced. For example, at the first step, I have the sun and photosynthesizers that convert solar energy into biomass, primary production. And at the subsequent steps, I have other organisms that convert primary production into biomass of higher trophic levels, for example, herbivores, or consumers, maybe carnivores in this case. The impressive fact is that to a decreasing quantity of production, produced energy corresponds an increasing quality of the energy produced. So you may read this graph by saying that we are increasing the quality. And for example, we have employing factors 100, 1000, and 10,000 for describing the quality of energy. And at each step of the conversion, I have a lesser quantity of energy produced of higher quality. So at each step of energy conservation, I have a part of the energy that is lost during the process of production, and the energy that is not lost becomes the production of this step. In particular, you may calculate some efficiency. You may recall that we have discussed the flow of energy on the biosphere, and we have introduced a figure of 0.2% efficiency in the conversion of solar energy. This means that 1 joule of solar energy is converted to another 1 joule of another type of energy with an efficiency of 0.2%. So this means that, for example, you need 200 joule to produce 1 unit, 200 joule of solar energy to produce 1 unit of primary production. At each step of the energy conservation chain, the efficiency of the process, as we already stated last week, increases, meaning that the organism or machinery that transforms energy in different types of higher qualities energy are more and more efficient in these conversion steps. Then there is another perspective that may be obtained by reasoning on the fact that when I observe primary producers, we always recognize that there is a certain quality of energy that is dissipated during the process of production. Dissipation means that, for example, solar energy is converted to thermal energy, and during this process of conversion, I have some new biomass or biological matter energy produced. And this sometimes is described by the second law of thermodynamics that establishes that there is the so-called arrow in time that allows us to distinguish between past and future. In classical mechanics, classical physics, we do not distinguish between past and future, meaning that all the processes that happen in one direction in time are equally possible in the reverse direction in time. When we start employing the thermodynamic paradigm to describe the transformation of complex systems, then we recognize that in reality, if we look at a process taking place in one direction, the process taking place in the reverse direction is not equally possible. Example is if you walk by a table on which you have a glass of water. If you give a bump to the glass of water falls onto the floor and breaks in thousands of pieces. And this is what you expect. You would never expect to come into a room with tons of broken glasses on the floor, and you see these broken glasses become assembled and jump onto the table as a glass or as a container. So this is the manifestation of the second law of thermodynamics, what tells us that the direction of evolution of isolated system is that the increasing of disorder of the system. And as a matter of fact, we may measure this tendency to disorder by introducing a new state function that describes the fact that spontaneous processes follow predetermined directions. This new state function is called the entropy. And we define the entropy by saying, first of all, it is a state function. This means different states have different entropies. It is an extensive function, meaning that if I have two systems with two values of entropy, and if I put the two systems together, the total entropy is the sum of the entropies of the two subsystems. And then it is recognized that if entropy of the if the state of the system varies, then the variation of the entropy may be indicated by the S is due to a quota that is related to external processes, external to the system, and the quota that is related to internal processes, internal to the system. And the second law of thermodynamics tells us that we have only for external variation of the entropy due to external processes, we have a formal way of quantifying this variation by writing that is equal, this variation is equal to the heat exchanged during this process divided by the temperature at which the exchanges takes place. For what concerns the variation of entropy due to internal processes, we may only say that the variation of entropy due to internal processes is always greater or at most equal to zero for spontaneous processes and is equal to zero for reversible processes. In particular, in the case of reversible processes, so processes for which the variation of entropy due to internal processes is zero, we may write that entropy is an exact differential as well, state function, and we may write this integral. We may be able to calculate this integral, summing the heat exchange divided by the temperature at which this exchange takes place, going from state A to state B. For irreversible processes, due to the fact that we recognize that the variation of entropy due to the internal processes is always greater than zero, for irreversible processes, we may only say that this integral, if we may be able to calculate it for irreversible processes, is necessarily larger than the integral calculating along same reversible along reversible processes that passes from one state to another. In this case, and I recall you, it is the only case in which we may really calculate this integral, we may calculate the variation of entropy of the system. All this reasoning just bring us to the conclusion that for an adiabatic system, so a system that cannot exchange heat with the surrounding environment, I recall you the definition is this one. So for an adiabatic system, dq is equal to zero. So we have only a variation of entropy due to internal processes. The entropy can only grow or at most remain constant, as in the case of reversible transformation. Formally, we may write that the integral between state A and state B of this quantity, the quantity of heat exchanged divided by the temperature at which the exchange took place, is always larger or equal to zero. As a consequence, if you accept the fact that the entropy, that the universe as a whole is necessarily by definition an adiabatic system because the universe contains everything, so there's nothing else with which the universe can exchange, so the Q for the universe is always zero. In this case, the entropy of the universe increases. The second law of thermodynamics may be restated in this very fancy way by saying that the entropy of the universe always increases. So on all processes of thermal transformation, from one state to another, the entropy of the system rises. So this, as we have already realized, or as we have already strike, um, if you try to apply this view to ecosystem, so second law of thermodynamics applied to ecosystem tells us that for systems that are far from equilibrium systems, that means, sorry, uh, sorry, I have a problem here. Okay, let's see if I can, okay. We were saying that if we try to employ the second law of ecosystem, to apply the second law of thermodynamics to ecosystem, then we realize that, as we have said, that ecosystems are far from equilibrium systems, so for sure all the transformations are not reversible, or better, are irreversible. So we may, instead of describing the states in terms of entropy, we may describe the states in terms of entropy production. So the variation in time of entropy may be defined as the entropy production, and the second law of thermodynamics tells us the entropy production is always greater or maybe equal to zero. So P, or the entropy production, is the derivative of entropy in time, T, is a measure of energy dissipation. So we have a first indicator that allows us to somehow evaluate how much of the energy that is employed during the transformation of different qualities of energy, how much of the energy is lost due to the energy dissipation. The second law of thermodynamics may be recast in the case of ecosystems by saying that the system uses all available resources to help increase high quality energy storage locally. As you may recall, we said that ecosystem locally decrease entropy, thereby increasing the energy dissipation, or if you want, say it in other terms, or saying in worse terms, by throwing entropy into the surrounding environment. And this is a consequence or a measure of the energy dissipation. So graphically, we may say that the solar energy that is the basis of all energy transformation is partially dissipated according to the second law of thermodynamics applied to ecosystem, partially reflected, and what it remains locally is energy storage of higher quality. As a consequence of this way of looking at systems, we shall conclude that older systems dissipate more energy. If you think about that a little bit, it is quite evident that due to the fact that locally living systems tend to store energy of higher quality, this means that the external environment shall accept more and more energies of lower qualities, and this is an effect of energy dissipation. But if you want a representation of the energy dissipation effect due to the production of biomass. In order to understand better, we may give a look again at the processes of energy transformation. We in general distinguish between two categories of energy transformation, very broad, gross category. The first one is primary production, in which we have an energy balance. It may be written by saying that the solar energy employed is equal to the reflected energy, so this is lost, plus primary production, so new biomass, plus respiration, this is energy dissipated during the processes of primary production, while and this is the energy balance for lower trophic level, primary production, while for higher trophic levels, you may rewrite that the energy of food taken by the organism is equal to the energy of the biomass produced plus the energy that has been employed for thermal regulation or respiration plus the energy that it is lost by not assimilating food or but plus the energy that is lost during the process of energy transformation. This way of looking at the energy balances allows us also to recognize that all organic matter or biomass has, if you want, kind of uniform characteristics, and these uniform characteristics is described by the stoichiometric ratios, so the proportions between the elements that make up organic matter, in particular here, we have carbon, nitrogen, and phosphorus. The stoichiometric ratios for carbon, nitrogen, and phosphorus, in particular for the red free ratio that links the nitrogen and phosphorus relationship, we have that to 40 atoms of carbon corresponds 7 atoms of nitrogen and 1 atoms of phosphorus. And these are all consequences of the energy conservation principles. I recall you that we have introduced some kind of stoichiometric coefficient that allows us to evaluate the energy content for different types of organic energies, like for example plants, energy plants, biomass, algae, vertebrates, biomass, and so on. But also we may distinguish the energy contents in terms of the different types of organic molecules. We may, for example, subdivide organic molecules in carbohydrates, proteins, and lipids. And as I told you already, carbohydrates has a higher energy content, sorry, a lower energy content than lipids, and this is something that we all know. Okay, this has to do with the physical constraints, more or less. So you may say that the physical constant we shall or may apply to the conceptualization of my ecological model are, for example, the first law of thermodynamics, energy conservation, and the second law of thermodynamics, energy dissipation, with the formalisms that we have just discussed. Then there is another relevant category of constraints that we may call ecological constraints. These are constraints at another hierarchical level of the description. In particular, you may recall when we have built our first model of bacterial growth in a batch, we have introduced a constant with carrying capacity, but it somehow takes into account the availability of resources, but maybe nutrients limitation or the availability of space in the case of falling and so on. And all these availability of resources are modeled by introducing a quantity that, for example, in the logistic growth, we have indicated with N0, that is called the carrying capacity of the system, but is a limit that is linked to the ecological relationships into the ecosystems, and that may be somehow included into our description as into our system specification as the last system of disequalities, as we have seen in the system specification. Another category of ecological constraints are both formalized by allometric principles or allometric relationships. We have already seen some example of that when we were discussing calibration. For example, the relationship of proportion between metabolism and biomass for several order of magnitude of the biomasses or of the energy consumption, energy flows, metabolism, they all display a kind of power law with a 3/4 exponential power law. Means that I can plot into a log-log plot, for example, relationship between metabolism and biomass, and I obtain a linear interpolation of this relationship, and typically for living system, the linear the slope of this linear interpolation correspond to a power law with an exponent of 3/4. This brings us to quite a far theoretical discussion concerning the way we describe ecological systems or living systems. I may anticipate you that the three-quarter power law is linked to the fact that three is the dimension of space, and two is the dimension of surfaces. So if we have um, to a corresponding to an increase of to a doubling, for example, of a mass of a living organism, it corresponds not linearly a doubling of surface, instead corresponds to 4 times the surface. Um, I will pass you some papers about that. It is quite interesting. We will see how to employ these geometric relationships, but when we will construct um, models for metabolic growth models for higher trophic levels. Another important type of ecological constraints is that coming from goal functions or orienters, and these are very important in structural dynamic modeling. For example, energy, entropy, exergy, energy are all uh, thermodynamic potentials that may be employed as goal function as or orienters that describe the evolution of a living system. In particular, the energy, we have seen conservation of energy, so energy is conserved in case of the entropy. So a goal function is an indicator, or if you want, a state function and an indication of its tendency, where the state function should go. So the energy goal function tells us that the energy is conserved. The entropy goal function tells us that the entropy always increases due to the second principle of thermodynamics, while there are several other state functions like the exergy and the energy that try to include, for example, the exergy, the fact that there is energy dissipation during transformation processes. So the exergy somehow is a way of measuring the energy dissipation in the energy transformation step. Or the energy, embodied energy, is a description of the quality of different types of biochemical energy in terms of the quantity of solar energy needed to produce 1 unit of this higher quality uh, biological energy, bioenergy. Okay, we shall now conclude the discussion of today by making a short overview and discuss a little bit about stability and equilibrium. Because we have employed the terms of equilibrium several times, we have talked about thermodynamic equilibrium. Thermodynamic equilibrium is when nothing is changing in the system, is often called thermal death. But what are more interested for dynamic systems are dynamic equilibria. Dynamic equilibrium, the first one you may look at is the steady state. We have already cited some here. For example, steady state means that if we have a state function describing the status of a system, the state function is constant in time. This means that I can write that the derivative in time of my state function is equal to 0. This is the first time of equilibrium different from the thermodynamic equilibrium. Thermodynamic equilibrium, as I told you, is thermal death. In this case, we recognize that the system is indistinguishable from the environment. This means completely diluted into the environment. And this is the condition, if this is the condition of maximum disorder or maximum entropy. In between, there are several other ways. In particular, we may start recognizing that living system, ecological system are distinguishable from the environment because they are contained. So they may contain or bounded. So they may be seen as in a kind of static equilibrium. Constraints are imposed by the environment, and in particular, in condition in which we have zero entropy production, these are conditions for which we may define Static equilibrium was equilibrium in which we have a zero entropy production. Okay. A dynamic equilibrium instead is an equilibrium in which the entropy production is different from zero. We may have several different conditions, linear or non-linear equilibrium, depending on the intensity of the forcing, or if you want, depending on the distance from the thermodynamic equilibrium of the system state. In this case, we introduce some characteristics that allow us to describe or differentiate different types of equilibrium. For example, we talk about homeostasis. A system is in homeostasis when, for example, state function somehow describes oscillates around an average value. In the case of, and this is the case of linear, non-linear, zero entropy production equilibrium. In these cases, we measure the stability of equilibrium by introducing the two terms, the resistance and the resilience, that we have what we talk today a lot of, without knowing exactly what it is meant by resilience. Resistance and resilience are two different ways of measuring the stability of equilibrium. In particular, resistance is represented of how much, or maybe measured of how much a perturbation move the average status, homeostatic states of equilibrium from its equilibrium. So it is the inverse of the depth of this hole in the space of in the state space of equilibrium. For dynamic evolutionary system, we may introduce another way of measuring states of equilibrium for high complex system. And this is the homeoresis. Homeoresis is a somehow stable evolutionary or continuous or discontinuous evolutionary transitions. This is called homeoresis. Again, these equilibrium are characterized by introducing the two descriptors, resistance and resilience. If we have a perturbation that changes the state of my system from a state X, perturbation the X, and the state of the system is changing to an X tilde, if the perturbation is cancelled in a time interval T, then we measure the stability of this equilibrium by introducing the resistance. Well, the resistance is a kind of an elastic stability in which we measure how much we normalized, how much the variation of the state is corresponding to the value of the state. The resilience is a kind of elastic stability telling us that is defined by the inverse of the time needed for the system to absorb the perturbation. So a system that is highly resilient is a system that takes a very short time to go back to its original functioning after perturbation. So resilience has to do with the time needed to absorb a perturbation. On the contrary, resistance measures how much the state of the system how much the state of the system changes after the perturbation. A system that is very resistant is a system that whose state does not change significantly after perturbation. When we talk about steady state in ecology, we refer with the term of climax. We may say that the system may switch from one climax to another climax level. For example, I'm trying to indicate the climax with these dotted lines, dashed lines, and I'm trying to represent the fact that the system is maybe oscillating around a climax average, and then after a state change, the system may jump abruptly onto another climax. This is typical. An example of this is, for example, if you get sick, your climax may be represented in health condition. Your climax is 36.3 Celsius degree temperature, body temperature. When you get sick, your climax is switched by, for example, an increase in temperature, but as you know, it shall overcome 37.5 Celsius degree of body temperature. Um, so, as it is typical in living system, we may observe a state of that is pulsing in time. The oscillations may be generated by forcing, so by the upper hierarchical level in the long term, but may be also induced by elements, for example, in the food chain, which is typical for consumers. If you remember, the Lotka and Volterra systems was described competitions between predators, then you will see that in some cases, this competition may induce pulsing in time states. There is some indication that this pulsing capacity somehow may be seen as maximizing the performance of the system. Okay, we finish here with the introduction of the class, and we will start from first day to go into details of the various ecological processes that the environmental engineer shall know in order to build a meaningful ecological model or ecosystem model. In particular, the ecological processes, what we are going to study are physical processes. So we will give a look at mass and heat flows, advection, diffusion, dispersion. These are all things that you have already seen. And we will just see some way of modeling these physical processes. For example, the CSTR model, and we will see several examples of mass flow. We'll discuss sedimentation, resuspension, and light extinction, that are the most important physical processes in the abiotic part of the story that ecological modelers should take into consideration. Then we will switch slowly onto chemistry, so we'll give a look to some chemical processes, in particular chemical reaction, enzymatic reaction, and in particular the effects of temperature on chemical reactions. You may call the Arrhenius law, or we will look at adsorption, ion exchange, or volatilization, but may be seen as chemical processes. And then all of the final part of this class will be devoted on describing models employed for formalizing biological processes. So we'll discuss biogeochemical cycling of nutrients, oxygen, and so on. We will discuss primary production models like photosynthesis, algal growth, and so on. Secondary production like zooplankton or fish, that is the metabolic model, and we'll give also some details, some hints concerning ecotoxicology. With this, we finish here today, and I rest here in the class, waiting for your questions. And if you do not have any questions, then we shall stop lecture here, and we'll see next Thursday.